Hi guys, welcome to We Teach. So in this session we are going to discuss RLC series circuit and parallel circuit by using differential equation to get the transient period. Okay. So first RLC series circuit. For the similar RLC circuit, the voltage differential equation at the transient period is given by. So this is the circuit. V of t is the AC input and at t equal to 0 switch is getting closing. So L, R, L, C are closed in or connected in a series. Vc of t is the voltage across capacitor and Vr of t is the voltage across resistor. VL of t is the voltage across inductor. So if I apply KVL in this loop, so which is V of t is equal to VL of t plus Vr of t plus Vc of t. Okay. Now we know that Vr of t is nothing but R into I of t and VL of t is nothing but L into dit by dt plus Vc of t is nothing but 1 by c into integral I of t dt, right? This we know. So I have replaced it with Vr, VL, Vc. Now if I solve this, I'll get my V of t is nothing but root 2v sin omega t plus theta v. Okay. So that is V of t is root 2 sin omega t plus theta v. Now V of t is nothing but R into I of t plus L into dit by dt plus 1 by c into integral I of t dt, where V of t is nothing but, so if I differentiate both sides with the t, I mean this equation, I am differentiating both sides with respect to t, okay. So now this become V dash of t, so first differentiation, so R into di by dt plus L into d square I by t by dt square plus integral and differentiation gets cancelled, which is 1 by c into I of t. So this equation is the second order differential equation and has solution given by. So this is the second order differential equation because there is a highest differentiator which is d square I of t by dt square. That's why this is the second order differential equation. Now my total response is I of, since it is a series circuit, so total response is I of t is equal to steady state current plus transient current. Okay, where ISS of t is the steady state current, ITR of t is the transient current which is decaying current with time. So to get ISS of t means a steady state current, so VR of V equal to I bar plus R plus J I into XL minus J I into XC. So from this I am writing I bar into R plus JXL minus JXC, right? So this I can write it as I bar into J bar. So where J is nothing but R plus J into, where J is nothing but R plus J into XL minus XC, right? This is the impedance, total impedance of the circuit. So if I take the magnitude, which is square root of R square plus XL square, XL minus XC whole square, and coming to angle between these three is phi equal to tan inverse of XL minus XC by R. So I is nothing but, so from there we know V and Z. So I is nothing but V at an angle theta V divided by Z at an angle phi. So V by Z at an angle theta V minus phi. So from there ISS of t is nothing but root 2 into V by square root of R square plus XL minus XC whole square sin omega t plus theta V minus phi. So this is the transient state current. Okay. Now this is the steady state current. To get transient state current, we solve the homogeneous differential equation. The homogeneous differential equation is obtained by setting the force equation to 0. So this above equations I am making to 0. I mean I am doing, this is the short circuit. To get transient current, I am making the circuit is short circuited, means supply getting short circuited. So from there I0 equal to R into ditr of t by dt plus L into d I square ITR of t by dt square plus 1 by c into ITR of t. This equation I can rewrite as d square ITR by of t by dt square plus R by L into ditR of t by dt plus 1 by LC into, so just I am rewriting the equation from d square plus d plus constant equal to 0. So if I write in a standard form, which is this one, now this equation has the general solution with the form of, since it is a second order differential equation, so this is the form of transient current as per our differential equation method from mathematics, which is k1 e power s1 of t plus k2 e power s2 of t, where s1 and s2 are the different roots. Okay, k1 k2 are the constants determined by the initial conditions like capacitor voltage and inductor current. Now s1 and s2 are the characteristic equations. So if I write these above equation in s domain, which is s square plus R by L into S plus 1 by LC equal to 0. Now compare this with our standard equation, which is s square plus 2 zeta omega ns plus omega n square equal to 0. So if I compare these two, from here I am getting my natural frequency omega n is equal to 1 by root LC, and if I equate this S term, 2 zeta omega n is equal to R by L. So from here zeta is equal to R by L into 1 by 2 omega n, right? So from there I can write it as zeta is equal to R by 2 into root C by L. So this is known as a damping ratio, where omega n is the natural frequency and where zeta is the damping ratio. Now from this equation, if I find the roots of the above equations like S square plus R by L into S plus 1 by LC equal to 0. So if I compare this with ax square plus bx plus c equal to 0 with our standard second order equation. So to find roots of this one, which is minus b plus or minus square root of b square minus 4ac by 2a, right? This is how we'll find the roots of a standard second order equation. So apply the same formula to s square plus r by l into s plus 1 by lc equal to 0. I'll get S1 and S2 is equal to minus 2 zeta omega n plus or minus square root of 4 zeta square omega n square minus 4 omega n square by 2. Now if I consider this is plus or minus, so if I consider S1, which is minus zeta omega n plus omega n into square root of zeta n square minus 1, and S2 is minus zeta omega n minus omega n into square root of zeta square minus 1. So these are the two roots we got from the above standard equation. Okay. Now, depending upon zeta, there are three cases are possible. First one is overdamped case. When zeta greater than 1, so this zeta is greater than 1, it is a overdamped case. The roots of the characteristic equation are real and distinct. Then the solution is become transient current is equal to k1 e power s1t plus k2 e power s2t. So in this case, we say that circuit is overdamped. Whenever zeta is greater than 1, it is overdamped, right? Now second case, it is critically damped. In critically damped, if zeta is 1, then that known as, or the system is known as critically damped. So the roots of the characteristic equation are real and equal. So in this case, roots, suppose zeta is 1 here in this one. So this entire term will become 0. So now my S1 and S2 both are equal, right? So which is minus omega n, which is real and equal. So the solution becomes ITR of t is equal to k1 e power s1t plus k2 e power s2t. Sorry, S1 and S2 are both are same, right? So S1t and S1t. In this case, we say that circuit is critically damped. Next, coming to third case, underdamped case. When zeta is less than 1, then that is underdamped case. So the roots of the characteristic equation are complex. In this case, roots become complex. In other words, the roots are the form S1 equal to minus zeta omega n plus j omega d, S2 equal to minus zeta omega n minus j omega d, where omega d is the damping frequency, which is square root of zeta square minus 1 into omega n. Okay, omega d is equal to omega n into square root of zeta square minus 1. That is the damping frequency. This is known as damping frequency. So for complex roots, the solution is the form of ITR of t is equal to k1 e power minus zeta omega n of t cos omega dt plus k2 e power minus j omega n t sin omega d dt. So this is the very important. When zeta is less than 1, the circuit or system is underdamped case. Transient current is nothing but k1 e power minus zeta omega n t cos omega dt plus k2 something. So in this case, we say that the circuit is underdamped. When zeta is less than 1, the circuit is underdamped. Next, fourth condition is undamped system. When zeta is 0, the circuit is undamped, means R is 0. Zeta 0 means zeta is equal to R by 2 into square root of C by L. So from here, zeta is directly proportional to R. If zeta is 0, then R is also becomes 0, right? R is the roots of the characteristic equation are imaginary roots. So in this case, roots are imaginary. In other words, the roots are of the form S1 equal to j omega n and S2 equal to minus j omega n. So these are the roots. So for imaginary roots, the solution of the form is ITR of t is equal to k1 cos omega n t plus k2 sin omega n t. So in this case, we say that circuit is underdamped or oscillatory also. Undamped or oscillatory means it will be like this. So these are the four cases based upon zeta. So if I see the overall, if zeta is 0, zeta is 1, zeta is greater than 1, zeta is less than 1. So in zeta is 0, then it is undamped. If zeta is equal to 1, which is critically damped. If zeta is greater than 0, I mean 1, which is over damped. If zeta is less than 1, which is under damped. So these are the 4 cases based upon zeta. Okay. So these are the respective transient current response under 4 cases. When zeta is 1, greater than 1, which is over damped. So this is how transient current look. When zeta is equal to 1, which is critically damped. So this will reach to 0. Now when zeta is less than 1, which is under damped, I mean first it will oscillate, then coming to steady state like that. When zeta is 0, it is undamped, means there is a complete oscillation will happen. Okay. So these are the transient current waveforms based upon different zeta. I mean zeta equal to 1, zeta greater than 1, zeta less than 1, and zeta equal to 0. Transient current response under different zeta values for undamped, overdamped, critically damped, and underdamped systems or circuits. So with this I am concluding the session. Thank you.